How do you get? Now? You get what? Okay, 2 sine theta cos theta. So you're deciding to put this like this. Cos. Anyway, differentiate this, I give you 2 sine, which is sine 2 theta. Okay. It's okay. Okay. So at the end of the day, you still got 9 gammas. Okay. So the gamma that is more troublesome is just that first one. The others are easier to get. Okay. So you're on a very good footing. On a very good footing. So were you able to get some of the gammas in literature? And some of the G's in literature, some of the metric tensors in literature? Okay, you'll be able to do that today. So that we'll finalize that tomorrow. So in that case, maybe you do 2-2. Each person 2. For Riemann Christopher, we don't have much to do. Once we get the Ricey tensor, and we'll get the curvature scalar, we can get our field equations. So it will now be left for us to appreciate our field equations. Okay. So we'll need at least 2-2 from you. So that with that 2-2 we can be able to come out with something interesting. Okay, and remember, there should be metrics where there is spherical symmetry. Don't just pick any metric. Okay? There should be metrics where there is spherical symmetry. Not just any metric, but metrics where there is spherical symmetry. Okay? So as we said yesterday, our problem is that of field equations interior to spherically symmetric okay. My guy is asking me whether it's exterior or interior. Is it exterior or interior? What's the difference between exterior and interior? What's the difference? Actually, it can be exterior and it can also be interior, depending on our definition of R. Okay? If our R is less than A, then we are dealing with an interior metric. But what we want to consider is where the exterior of the star is not populated. Are you getting the point? It's only the star's interior that is populated, that is dense. The exterior is not populated. Okay, it makes our it makes our problem easier. If we consider an exterior that is populated, it will be more complex. So what happens is, if you go through that book, that Inside Stars, okay, you will discover that the assumption that has been made there is that the star is denser than the surrounding. So if the star is denser than the surrounding, then the surrounding is considered to be Schwarzschild, that the Schwarzschild metric can describe the surrounding. Because the Schwarzschild metric is that for a normal gas. So it's considered when you leave the surface of the star and you are outside, the Schwarzschild metric can be used to describe the space around there. Okay, so we are considering a star that is highly populated, then we restrict ourselves to the interior metric. But if we want the surroundings to also be populated as the same way as the star is populated, then this, we can use that same metric tensor to describe the exterior. Okay, but it's going to be a complex problem to solve. Okay, it's going to be a complex problem to solve. So this time around, we'll restrict ourselves to the interior, where R is less than A. Okay, so we have our, I can see your Riemann-Christoffel tensors. Okay. So how are you doing your permutations? To make sure that you don't leave out any of the Riemann-Christoffel tensors. I'm seeing the first one with the R1. What about R0? Why do you start with R1? Why do you not start with, then you permute all these things? Did you do that? Huh? Remember, we also have gammas that are 0 up there. We have gammas that are 0. So we also expect R with 0 up there to exist. Did you do that? Okay, we are able to do that. For okay, so you can have 0, 0 here. Then you now permute these two. Then later on you change this to 1 and permute these two. Okay, so you have this as 0, and then you have, let's say, A, B here. You can write it out and try to see what it will give you. Okay, and see whether any of them will survive. You quickly substitute for A and B, A and B, A and B, without necessarily carrying out the calculations. Okay, you quickly substitute for A and B, and see whether any of them will survive. Okay, the one that will survive, you can note it. You can note it and then you now write the complete expression for that one. Okay, so how many of them survived? For the 0. For the 0, how many survived? I'm seeing 0, 2, 2, 0. Okay. The way I've written them, there's no order. I said there's no order. You are writing 0, writing 1, and so on. When you start with 0, make sure you go through all of them so that you don't end up leaving any. Okay? Because once you leave just one, it compounds your problem. So when you start with 0, just go through all the zeros. Okay? So you permit these ones and then see. So I can see R0, 0, or R0, 2, 2, 0. R0, 2, 2, 0. Okay, so what you are using is, where is it? And you remember there is also differentiation here. Okay. There's also differentiation, although it's only with the first 2 terms. The other last 2 terms is multiplication. So you have R sigma alpha beta gamma, the same as that, sigma alpha gamma comma beta, minus that, sigma alpha beta comma gamma, plus introduce another variable epsilon, alpha gamma, then you have sigma epsilon beta, minus, you now have epsilon alpha beta, then you now have sigma epsilon gamma. So now have this one. Okay. So let me see. Saying R R0220 will survive. With what you have done now, it's difficult for us to verify whether you were able to capture all. Okay, so if we had set this to be 0, for instance, then we set this one to be 0. Then we have our beta gamma. So here we're going to have 0. Okay, what is 0? Alpha. 0. Then we have gamma, comma, beta, minus, we have 0. Our alpha is 0. Okay, our beta remains. Then comma, gamma. Then we have plus epsilon. Our alpha is 0. You have gamma. Then we have 0 here. Epsilon, beta. Then minus epsilon, our alpha is 0. Beta. Then we have 0. Epsilon, gamma. So this is what we are going to have. Okay. Then we'll now go back to our gammas. We'll go back to our gammas and see which of the gammas are non-zero. Okay. To eliminate the first two terms, because the first two terms have 0 up. So we'll go back to our gammas. Okay. We'll go back to our gammas to see. So we'll come back to our gammas. Okay. There's no gamma with 0. Where is it? There's none with 0 up. Okay, I have 0, 1, 0. 0, 1, 0. Okay, so that's the only one that will survive here for this. So it's 0. We have gamma 0, 1, 0. Okay, so what we are expecting is that this can be 1. Okay? We're expecting that this can be 1. And if this is 1, for our gamma is 1. Okay? We know that our 0, 1, 0 depends only on R. Have you seen that? Our 0, 1, 0 depends only on R. So we also expect our beta to be 1. Okay? So we expect our beta to be 1. Then what we are seeing is we have R, 0, 0, 1, 1. Is that not? So it will now give us 0, 0, 1, comma 1 minus 0, 0, 1, comma 1 plus epsilon, gamma epsilon 0, 1, 0, epsilon 1 minus epsilon 0, 1, 0, epsilon 1. Okay. Does this survive? Will it survive? Look at this. This is the same as this. This 2 is the same as this. Okay. So this will be 0. That will be 0. That one will not survive. Okay. So that's the only possibility we have. Which other possibility? Okay, we have 0, 2, 2, 0. What about 0, 1, 1, 0? Okay, it's also there. Okay. So we have so when this is 0, we don't have any. So we'll now go to the next when this is 1. Okay. So we'll now have, so in place of 0, we'll put 1. In place of 0, we'll put 1. Okay. No, 0 will remain here, but we are only changing this. So in place of this, we put 1. We put 1. We put 1. 1. 1. I think that's that. Then okay. So again, with the 0 up, what will happen is that one of these will be 0, one of them will be 1. Is that not? So if our beta is 0 and our gamma is 1, that's only when this will survive. Okay? So if that is that, then we are going to have R 0, 1, 0, 1. Okay? 1, 0, 1. Which is the same as we have 0, we have 1, we have our gamma is what? 1. This one is not there. This one is not there. Minus 0, 1, 0, comma 1 plus epsilon 1, 0, 0, epsilon, beta is 0. Okay, minus epsilon 1, 0. Then we have 0 epsilon gamma, which is 1. So we have this. Okay. So this does not exist. This one does not exist. Is that not? So this one will go off. But this one exists. Okay, this one exists. And then this one, if epsilon is 0, this one will survive and this one will be 0. If epsilon is 1, do we have 1, 1, 0? Do we have 1, 1, 0? We have 1, 1, 0. So what will happen is we are going to have minus of this plus okay, you don't have 1. I'm seeing only 1, 0, 0. Is there no 1, 0, 1? Did you check 1, 0, 1? I didn't survive. You did not survive. You check 1, 0, 1. Okay. So we have this. So again, you are saying 1 will not survive. And automatically 2 will not survive. and also 3 will not survive. Okay? If you come here, 0, 0 will survive. Is that not? So you have plus or minus 0, 0, 1, 0, 1, 0. Is that not? When you go to 1, it will not survive. 2, it will not survive. 3, it will not survive. So this is our final expression for R0101. Let me see what you got. You're just giving me the final expressions here. What do you get for R's? What do you get for R0? I'm seeing your R0110. And there's a term there that I am not convinced. So let's do that one and see. Okay, let's do the case where beta is 1, gamma is 0. Okay? Where beta is 1, gamma is 0. So in that case, you are going to have that. That's what I'm saying. I want to do that one. Our beta was 0 before. I've just changed it now so that we do the next one. So that we'll do the case where we have R0110. So this is the one we want to do now. Because actually this one is supposed to be minus of this. It's supposed to be minus of this one. So let's see how it comes out. So in that case, we will now have so we are starting from here. Okay? So we have 0, we have 1, our gamma is 0, and our beta is 1. Okay? Minus 0, 1, our beta is 1, comma 0. Okay? Plus, we now have epsilon 1, our gamma is 0. Okay, then we now have 0, epsilon, our beta is 1. Okay, minus, we now have epsilon 1, our beta is 1. And then we have 0, our epsilon is there. Then our gamma is 0. So we now have this one. Okay. So from there, this one will survive. This one will. Do you have 0, 1, 1? We don't have 0, 1, 1. Okay, comma 0. Because it's dependent with time. So it will not survive. Okay. And then this one, if I have 0 here and 0 here, it will survive. So I have 0, 1, 0, comma 0, comma 1, plus So 0, 0 will survive. So I'll have 0, 1, 0, 0, 0, 1. So I'll have this. So that one will survive. Is that not? Then if I go to 1, it will not survive. We don't have 0, 1. We don't have 0, 1, 1. So this one will not survive. You go to 2, it will not survive. You go to 3, it will not survive. And then if you come here, 0, it will not survive. 1, will 1 survive? 1 will survive. Okay? You have 1 and 1 here. So this one will survive. So you have minus 1, 1, 1, 0, 1, 0. So you have that one. Okay? This term like this, we are supposed to get a similar term here. You can see that there's evidence of minus. Look at this term here. It's with a plus. This other term here is with a minus. The one here is with a plus. So I expect to have a similar term like this here. So where did we not get it? Where did we not get it? So you have this one is which one? That is supposed to be. Let's see. Here our gamma was 1 and our epsilon was 0. Is that not? So if we have that, so we have, remember the 1 is already there. So our gamma is 1, our beta is 0. Here our beta is 0, our gamma is 1. Okay? Then here our gamma is 1. This is where we made the mistake. This is 1. Our gamma is 1. Our beta is 0. So this is where we made a mistake. Okay, that's where we made a mistake. So that when you now take 1, 1, you have a plus term here. You have a plus term here. 1, 1, 0, 1, 0. So you see this is the negative of this. Because if you change the indices of any two, the last two indices, there's a minus. That's R, alpha, beta, gamma, sigma is equal to minus R, alpha, beta, sigma, gamma. It's a non-relationship. Okay, it's a non-property of this tensor. So I was expecting this one to be minus of this one. So once you get one of them, you don't need to get the other one. You just take the minus, it will give you the other one. Okay, you just take the minus, it will give you the other one. So once you get the beta gamma, you don't need to get gamma beta. Gamma beta will just be minus of beta gamma. Okay, so you see how careful you need to be. Okay, so this is your own expression here. Is it the same? 1, 1, 1, 0. We got this plus this minus this is correct. Okay, so the one that is missing is this one. So once you get this one, you automatically deduce this one. Okay, it just become a minus of the other one. Okay, So like most of them that you got here, where you have maybe R2332, then automatically there will be R2323. The last two indices, you interchange them. Okay? Right, this is what we call it the antisymmetric property of the Riemann-Christoffel tensor. Okay, it's the antisymmetric property where a change of indices introduces a minus sign. Okay, so we have that. So all these ones that you have. So this is for 1. Okay, when you go to 2, you equally get. When this is T0, then you also go to 3. So if you take it systematically like that, it will be difficult for you to make a mistake. So once you start with 0 here, you deal with 0 down here. Once you start with, and then you change this to 1, change this to 2, still with the 0 there. Then you change it to 3 and get all of them. Okay? So, so we have this for that. So what you will do for me is just to check this again and be sure that you have left out none of them. Okay? As for the substitution, I know it will be very easy for you to do. For the substitution, it will be very easy for you to do. But we can leave it like this till the last stage. And then just substitute at the last stage and appreciate. So you can leave it in terms of the gammas like this. Then when you get to the last stage, you now substitute the gammas and then you now appreciate what is happening. Okay? So after getting this, our next step is to get our Ricci tensor, which I said is easier to get. It's easier to get. If you can get this, then that one is not an issue. Okay? So how do we get that one? How do we get that one? What does the formula say? That for you to get R, alpha, beta, how do you do it? It's equal to G. I'm talking about alpha, beta, you're telling me of 0, 0. G. Huh? G. So how do you do it? Where do I put my alpha, beta? Yeah. And then I have what here? Huh? Do you have alpha, beta? Do you have the formula there? Where is it? Give me. Write it for me. Don't want to use energy. Take this other one. Take this. It's not correct. Let me see what you have there. Where is it? Yes, this is correct. This is correct. This one is correct. It's so you just set this to be equal to this to give you that. Okay? So if you and remember there are 16 of this. Okay? So if I want my R00, I will have R sigma 00 sigma, which is the same as R 0000 plus R 1001 plus R 0022 plus R 3003. Okay, then I will go back to my Riemann-Christoffel tensor and see which of them will survive. Okay, so looking at this one, will any of them survive? The last, this one. 1, 2, and 3 will survive. So yeah, this one will go to 0. So your equation will reduce to this. Then from there you can now substitute all of that inside. Okay? Now substitute the expressions for this, this, and that. And as I said, you can still leave them in terms of gamma. Okay? If you want to handle your gammas at one time. You will get the same thing. You will get the same thing, but it's just that as you are substituting, it's expanding. But once you substitute at once, okay, it gives you. Well, you can decide to substitute at this level. You can decide to substitute even at the end in the field equations. So it depends on you which one is easier for you to handle, because it's very easy to make mistakes with those R, G, and whatever. So the best thing is to leave it at the end. You now put them, you now feed them inside. Okay, so you check all of them for all the 16. Okay, so you check all the 16 and see the ones that will survive. Okay, so the number of these that will survive will determine the number of field equations that will survive. Because your field equation is R0, R alpha beta minus half R G alpha beta equal to a certain constant K T alpha beta. So that's your field equation. So the number of these that will survive will exactly give you the number of field equations that you expect to work with. Are we together? So from this one, you will now know how many field equations you are dealing with. You now know how many field equations you are dealing with. Whether they are 4, whether they are 5, whether they are 6. Okay? So, and then to get your R, that's when we now bring in the G. R is G alpha beta R alpha beta. That's when you now get your R. Okay? With that. So the R now will be determined by the surviving this and this. So you get your R. Once you get your R, then you have gotten all you need on the left hand side of our field equation. Okay? We have gotten all what we need at the left hand side. So our issue now is the right hand side. Our issue now is the right hand side. So what do we do? There are different types of stress tensor. Different types of stress tensor. So you need to assume your mass to be of a certain type. Okay? And the easiest type to handle is a perfect fluid. Okay? It's a perfect fluid. So you assume that what is inside the star or whatever is a perfect fluid. Okay, then you can use the stress tensor for a perfect fluid. So you now bring in the stress tensor for the perfect fluid and insert at the right hand side. Then from there we can start. We have already had our field equations. Then we can attempt a solution. Okay? We can attempt a solution. Just getting the field equations is good enough. Okay, it's good enough. And then we can now attempt a solution as well. So I expect us to be able to get here tomorrow. Okay, so you'll be able to get this and this from me. And then check this online. Check the stress tensor for a perfect fluid. Check the expression of a stress tensor for a perfect fluid. No, it's just K. I just use it to represent whatever is there. I think it's something over C to the power. It's something like that. Okay. So I think we are good to go. Okay. Any question? Any question? No, our problem we decided to work on was the field equations. Okay, so from the gammas, if you want to go to the geodesic equations, you can equally go. We will get equations of motion of test particles. Okay, you will get the equations of motion of test particles. But this will give us the field equations. Okay, it will give us the field equations. You look like in a gravitational, in Newton's theory, the field equation is F equal to minus. That's the field equation. Okay, that's the field equation. So phi, the potential, what phi is playing in this equation is the same thing G is playing in this other equation. Okay, so these are the field equations. So this actually describes the field. They are the field equations. Okay, so we'll end there for today. So the task for this evening is getting this, and looking for this online. And then plus the two papers you have to look at. Okay, you want to finish this first? No, you do all. Otherwise, we will not leave this place tomorrow. That's what I'm saying. Otherwise, if we start by 9,
will only leave here by 6 tomorrow. So it's better you reduce the work. If you don't reduce it, we are leaving this place 6 tomorrow. Okay. It's okay. So we'll continue from there tomorrow.